We're going to see now this example that you see on the board. This is an operational amplifier that will that we are supposed to find the relationship between the output and the input. Okay, so let's work this out. The first thing that we gotta do, as I started doing, is to put the impedances of this element. Remember, this was 1 over C S. This one was just R. Let's call it R2. This would be and then we have, this is R, of course. This one right here would be 1 over CS. And then this also R. So you have 1, 2, 3, 4 elements. That's a good number. So what the concept of impedance, you would say for impedance, for the impedance calculations, let's do that, what we're gonna do. So that's this here. This is like, I would say, it is like, let's just take this one right now. This is like if you were to take this C element in here and you take this R and you put them together like this. Okay, but this is going to be related to the impedance form, which is going to be like this. The impedance form, this is in here, you have C, there's a C in there. And then you have an R element over here. Okay? So what I can do is write this in terms of the impedances. This were in the time domain. In the impedance here, I will say, okay, look, this is like 1 over C times S. Okay, and the other one is like R1. If we treat this as a parallel circuit made out of resistors only, you will see that you will reduce to this, but think of the elements as a whole, because now this in reality is this. Okay. Let me just erase this for a moment here to make it clear. And so we go over here and we say, okay, draw this please. What you have is you're going to reduce it in such a way that this whole thing looks like this, and this we're going to call it Z, the impedance, Z1, okay? Do you remember if this were to be treated like if it were resistors? Do you remember how you handle when they are in parallel? I am sure you remember that you know that 1 over the impedance, Z1, it will have to be 1 over the impedance first, 1 over C, CS, plus 1 over R. Okay. The other one was plus 1 over R1, right? Like that. So from here, you can deduct from this equation. Can you find out what the value of Z is? And so let's just find the value of C. So this would be 1 over Z1 is equal to CS like this. Plus 1 over R1. Okay, so that is this. Now we reduce this, we should be able to do something nice as well. And then let's just go ahead. If you have now the resistor here, if you have it like this, and then C like that. So you can find out what the impedance of the entire thing would be, because that's what we want. Remember that in this case, the transfer function that we want, let's see, this is the C element and this the R. Okay, so once this is as if you want to transform it into a big resistance, and that big resistance you're going to call it Z. Right, you're going to call it Z. And obviously you could put the impedance here as 1 over C to L, and this one would be IR, like this, voltage. Okay. So this is the input, the impedance Z sub 2. So Z2 is going to be equal to R sub 2 plus the other one that was 1 over C 2 times S. So one experiment that we can do is to obtain the transfer function, obviously. In this case, you have that the this ratio of the Z2 minus R1 called the transfer function. The transfer function, this is Z R, this is the transfer function is minus R2 over Z1, Z2 over Z1. And this is going to be equal to R2 plus 1 over C S okay, so that's what this is. So you could do this. You could get this transfer function written as, this would be R sub 2 plus 1 over C sub 2 times S and then the term on the bottom is going to be curious because this one is going to be 1 over CS C1 is so this will be CS our CS this is C sub 2, this is sorry, we need to fix something here. So this is going to be here. Yeah. So this is 1 over CS plus 1 over 1. 1 over R1. So if you try to do this in symbolic form, you can. You just need to do the right products and make sure that this is in the right form. So this we could say minus minus C1 S plus 1 over R sub 2 and then times R2 into plus 1 over C sub 2 times S. So that's how the transfer function is. Now you could simplify this, and to simplify this would be an R2 C sub 1 S times R1 of S, and then you have C sub 1 R sub 5, C sub 1 R1 of S and then you have plus R sub 2 C sub 2 S, and then plus 1. So you could simplify this a lot, because you can always write it in terms of, let's see, of factors that are common. So this is going to be divided by R1 C sub 2 times S. So if you do this, the way I have it implemented in my example is like minus 112, no, 1.223. So we have the expression in here, and now let's see. I'm just replacing the values that they gave us. This is going to be S squared plus 45.9 S plus 2235. And then this divided by S. So this is called a proportional integral derivative control. And let me show you why that is. Let me show you what that is. See here, the transfer function is made of a gain which is normal. Here this is 1.232. And then you will have S squared plus 45.9 S plus 22. Yeah, and then this divided by S. This expression is called a PID controller. Now, I think you may challenge me and say, well, how come that is a PID control? If you multiply the factors, you're gonna have minus 1.232 S, right? And then you will have plus 1.4, yeah, 1.432, and then no S, because we will, sorry, I have a mistake in here. Let's just correct it real quick. Okay, so that's this is 45.97, and this is plus 22.58 divided by S. So this thing is the derivative control. This is the proportional control. and this is the integral control. So this is the derivative control, the proportional control, and this the integral control. So I think with that we cover how to get the transfer function for this other system that is a little different than the previous example. I thought it was running.